Hello viewers, we're now taking you through the story of A-Level Physics Paper 2. And this video we shall look at the entire calculations on capacitors. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we start, let's look at the course outline for this paper. So Physics Paper 2 is divided into 4 parts. The first part is geometrical optics, where 2 questions come from these topics and the student must answer 1. Next is physical optics or waves, where 2 questions come from these topics and the student must answer 1. Then the third part is electrostatics and electricity, where 3 questions come from these topics. And the fourth part is magnetism and AC, where 3 questions come from these topics. So a student can decide to choose 2 from here and 1 from here to make the 5 questions which are required. Or you choose 1 from here and 2 from here to make the 5 questions which are required. So any is okay. So in this video we shall look at all these calculations. First we shall look at calculations of capacitance of a parallel plate capacitor. Then we shall go to calculations of energy stored in a charged capacitor. After that we shall go to calculations of capacitance of an isolated charged sphere. Then after that we shall go to calculations on arrangement of capacitors in circuits. Then go to calculations on joining two capacitors. And lastly, calculations on dielectrics in capacitors. So all these calculations will be covered in this video. So we are interested in the calculations, but notes are also available in this book called Mastering A-Level Physics Paper 2. So this book contains notes, worked examples, and try questions on all the parts of Physics Paper 2. But this video shall concentrate on the worked examples found in this book. If you want a copy, you can get it by contacting this author. Other books are also available. For example, if you are a student offering physics, you will need 3 books. There is one of Physics Paper 1, which is this, Physics Paper 2, which is this, and Topical Question Bank, which is this. If you are offering also Principal Mathematics, you will need a book of Math Paper 1, which is that, Math Paper 2, which is this, and also Topical Question Bank. Then if you are offering physics and submath, then you need a book of submath, which is this. The rest are for O level. So now we can start our topic. So now we can start our topic of capacitance or parallel plate capacitor. So we need to know what a capacitor is. So capacitors are devices used for storing charge. So this is known there. They are used to store charge. That's the main purpose of a capacitor. So they are used in many electronic gadgets like radios, televisions, and other devices which require storing charge. And here they consist of 2 metal plates separated by an insulator called a dielectric. So I think you saw in the part of calculations, the last part was about dielectrics. So that's why I shall concentrate more on what a dielectric is. But for now, just know that it is an insulator. So when we are drawing a capacitor, we use what we call a schematic symbol. So here the symbol will be these 2 vertical lines, but they are equal. So it's different from a dry cell. For a dry cell, the lines are not of the same length or height. One is longer, which denotes a positive polarity. Another is negative, which is shorter, which denotes a negative polarity. But when it comes to a capacitor, both must be of the same height. As you can see it here, they should be of the same height. So that's the difference between the symbol for capacitor and that of a dry cell. So these are what we call the plates. And now this, what you see here, is a diagram of real life capacitors. So these are various types of real life capacitors. I think if you open your radio, you'll be able to see most of these gadgets here. So those are what we call capacitors, and the main aim is to store charge. So now that we have known what a capacitor is, we can go now to the capacitance of a capacitor. So by definition, the capacitance of a capacitor is the magnitude of charge required to cause a change of 1 volt in the PD across the plates of the capacitor. So that's how the capacitor can be defined. Also, you can choose to define it in this way: that the capacitance of a capacitor is the ratio of the magnitude of charge on either plates of a capacitor to, so this is needed because we use the word ratio here, to the potential difference across its plates. Therefore, it implies that because we said ratio is like division, so ratio of charge, magnitude of charge to potential difference. So C will be equal to charge over potential difference. And when I choose to rearrange by taking this one this side, I'll come up with Q is equal to CV. So both these will be used more frequently in this video. So here we shall define the symbols. Q is the quantity of charge measured in coulombs. So that means that if charge is given in microcoulombs, we change it to coulombs. Then V is the PD across the parallel plates and is measured in volts. And lastly, C is the capacitance of a capacitor and is measured in farad. So farad is the SI unit of capacitance of a capacitor. But sometimes they can give you in smaller units. They can give you in terms of microfarad, which is mu f, picofarad, which is pf, or nanofarad, which is nf, small n. So how can you convert if you're in that form? You have to remember that 1 microfarad is equal to 10 to power negative 6 of farad, and nanofarad means 10 to power negative 9. Picofarad means 10 to power negative 12. So if, for example, they give you 6 microfarad, to change it into farad, you have to multiply it by 10 to power negative 6. If they give you 5 nanofarad, to change it to farad, you have to multiply by 10 to power negative 9. And if they give you, for example, 12 picofarad, to change it to farad, you have to multiply by 10 to power negative 12. So that's how you can convert. So before you substitute in the formula, you have to ensure that the capacitance is in farad. Now, what is a farad? So by definition, a farad is the capacitance of a capacitor when the PD across the capacitor plates is 1 volt, and the magnitude of charge stored on either plates is also 1 coulomb. So PD should be 1 volt and charge should be 1 coulomb. That will be a farad. So that was capacitance of a capacitor. Now we shall go to capacitance of a parallel plate capacitor. So in this case, what we shall consider 2 parallel plates of a capacitor, each having a charge across which a PDV is applied, and the separation between the plates is D, as shown below. So that means we shall need to make some illustration. So that will be one plate, and this is also another plate separated by a distance d and connected to a PDV. So we are connected to this PD here, which is V, and because it's connected to a PDV, there will be charge. So this will give this, because of this polarity of this dry cell, it will give this one a positive charge and this one a negative charge. Then electric field intensity will be in that direction, from positive to negative. So we already saw the relationship between electric field intensity and PD and separation. So you know that electric field intensity is equal to PD across the plates and the separation of the plates. That is, means that E will be equal to V over D. So we shall call it equation 1. Then we shall also let A to be the area of either plate. So the plates, the capacitor plates must have the same area. Q will also be the magnitude of charge on either plates, and epsilon will be the permittivity of the medium between the plates. So previously in electrostatics we talked about this permittivity, and I believe now you are conversant with it. So epsilon is the permittivity of the medium. Therefore, from Gauss's law, it implies that electric field intensity is equal to charge density on either plates over permittivity of the medium between the plates. Therefore, you shall come and substitute that electric field intensity is E, then charge density is this sigma, and this permittivity is this epsilon. But charge density is the same, is charge over area. So this one will be replaced by Q over A, and this one will remain. That's why there's this division sign. Then when I change this one to a multiplication sign, this becomes a reciprocal. That is why it is going down. So this will be equation 2, where E is equal to Q divided by epsilon A. Now I have two equations for electric field intensity, meaning I can equate the two. So when I equate the two, the equation 1 was this, equation 2 is this. So I'll come and do that. Then what I will do, when I bring this one this side and take this one here, I'll come up with this step. Then I remember that Q over V is equal to C, which is capacitance. When I remember that, I'll come and replace this one with C to come up with C equal to epsilon A divided by D. But most times, like I told you under electrostatics, we use free space as our medium. Therefore, we shall come and say that if the medium is vacuum or free space, then capacitance will be epsilon naught. So we use epsilon naught to mean permittivity of vacuum or permittivity of free space. And like I said, this is a constant that it will always be given in an examination, multiplied by A divided by D. So this is the formula we have been waiting for. So you must look for a way of remembering it. So in order to remember the formula, we need to go through a number of questions. So question 1 came from UNEB 2002 paper 2 questions 10b Roman 1, and says calculate the capacitance of a parallel plate capacitor whose plates are 10 centimeters by 10 centimeters separated by an air gap. Now air gap means the permittivity is free space of 5 millimeters. So 5 millimeters is D. The first thing to do is to quote the formula. Then you substitute. Like I said, this is a constant. Then this area will be given by this times this. But remember, area must be in meters squared. Therefore, this one convert to meters to give you this. Convert this to meters to give you that. Then also, The separation must be in meters, so convert it to meters to give you this. Then from there you can use the calculator to come up with the answer. So this will be the capacitance in farad. So that was question 1. What about question 2? Question 2 came from UNEB 2020, that is last year. Paper 2, question 10C, and says the plates of a parallel plate capacitor are separated by a distance of 2 millimeters in area. If the surface area of each plate is 5 centimeters squared, and a PD of 6 volts is applied across the plates, find the magnitude of the charge on each plate. So what we shall do, we shall say that charge is equal to CV. I think you remember that. Then from there we shall remember that our C is equal to this formula which we have already derived. Then we shall, but there is also still this V, so put it here. Then from there I'll come and substitute. So substitute for this constant, it is always given. Area, it was here, it should convert to meters squared by multiplying by 10 power negative 4. Then D, it was here, converted to meters to give you this. Then V, it was here, so substitute for V. When that is done, use a calculator and you'll come up with this as the answer. So SI unit for charge is coulomb. Then question 3 came from UNEB 2001, paper 2, question 9D, and says the plates of a parallel plate capacitor, each of area 2 centimeters squared and 5 millimeters apart. The plates are in vacuum, not this word vacuum, and a potential difference of 10,000 volts is applied across the capacitor. Find the magnitude of the charge on the plate, on the capacitor. So still we shall use the same formula. Q is equal to CV, where C is this. After that we shall substitute. Substitute for the constant, substitute for the area, substitute for the separation, and then substitute for the PD. When that is done, you'll use the calculator and come up with this as the charge they wanted in coulomb. So now we can start our topic, energy stored in a charged capacitor. So we shall need to derive the formula for the energy stored. So you shall suppose the PD between the capacitor plates at some instant was V, and positive Q was the charge on the positive plate, that is plate A, as shown below. That means we need to make an illustration. So this will be the PD between the capacitor plates, and these are the plates, plate A and plate B. They told you that plate A has a positive charge, and it depends on the polarity of this dry cell. If you interchange, then it cannot be correct. So the one which is the positive part of the dry cell will be connected, will make this charge plate positively charged. So when you are labeling the charges, these charges, you must be mindful of also the arrangement of this battery or dry cell. So at any stage of charging, V is equal to Q over C. So this is a rearrangement of the formula we saw in the previous video, because we saw that Q is equal to CV. That means that if I want to make V the subject, I'll take this C this side to give you Q over C. So a graph of voltage against charge will be as shown below. So we need to illustrate on the graph. So those are the axes. Then we shall draw the graph. It will be a linear one with a positive gradient, and to imply that when PD is V, charge is Q, and when PD is increased by a small change in V, charge will also be increased by a small change in V. So we are shading this area. Why do we shade it? We shall see in the next slide. So this is what I've said, that let the charge on the plate be increased from Q to small change in Q. And how do you do that? By increasing the PD. So it implies the energy supplied to put an extra charge or small change in Q on the plates is equal to the area of the shaded strip. So that explains why we were shading this part, why this part was shaded, to give you the energy supplied to put an extra charge of small change in Q onto the plates. So that small work done will be area. Now that area is a trapezium. If you look here, this shape is a trapezium. So the area will be a half H in brackets A plus B. So the H will be from here to here, and which is what? Which is small change in Q. And A can be from here to here, which is V, and B can be from here to here, which is V plus small change in V. So when you know that, we shall come here and get the area of a trapezium. So in this case, this will be the half, then this is A, this is B, and this is H. So what we are going to do, we are going to expand. When we expand, remember this and this is 2V plus small change in V. But remember, there is also a half outside. So this a half times 2V gives you V, which is here. And also here outside this bracket, there is another small change in Q. That is why there is V times small change in Q. Okay. Then there is also this a half times small change in V, which is here. But also outside the bracket there is small change in Q. That's what we put here. Then from there, remember this was equal sign, but when you come here, it will be as approximately equal to this. Now, why is it so? It is because these are two small changes. For example, if you multiply 0.0005 times 0.00005, those are two small values, so they approximate to 0. That is why the whole of this approximates to 0. If you do principal math, you will be able to understand this under the topic of error propagation. But for now, but if you don't, just remember that these two small changes, they approximate to 0. That is why you put an approximate sign to show that what you are remaining with will be only this. But I already know that V is equal to Q over C. So what I'm doing, I'm just rearranging. It implies that where there is this V, I'll come and put Q over C. But there's also this small change in Q, so to remain there. That is now small work done. What about the total work done? So to charge the capacitor from a 0 charge up to a charge of capital Q, the total work done will be given by integration. So you integrate from 0 to capital Q of this small work done. But what you realize is that this was small change in Q, but now when you put an integral sign, it becomes dQ, to mean that you're going to integrate with respect to Q. So when I integrate this Q, I'll come up with a half Q squared. So this is a half is this 2 because of a half, then this is 2 squared, but there's also a C here, so it will remain there. I'm integrating from 0 to 2, therefore substitute for capital 2 where there is small 2 to come up with this, minus substitute for 0 to give you 0, so it would be this minus 0, but it's okay even not to put this minus zeros because it remains the same. That is why I'm only putting this as the output of the total work done. And like we say, the total work done is the same as is the energy stored. It implies that this formula is the formula for energy stored in a charged capacitor. But there is also another form. We can also express this formula in another form. So if you remember that Q is equal to CV, I'll come here and say what will happen if I eliminate Q. So I'll come here and substitute for Q and come up with this formula. So this is also another way of expressing energy stored in a charged capacitor. So we have so first into expressions. And with those we can go through these questions. So question 1 came from UNEB 2007, paper 2, question 10b, and says a capacitor is charged by a 30 volt DC supply. When the capacitor is fully charged, it is found to carry a charge of 5 microcoulomb. Calculate Roman 1, the capacitance of the capacitor. Roman 2, the energy stored in the capacitor. So for Roman 1, we shall first say that Q is equal to CV. Therefore, when I substitute for Q and C I don't know, then I know V, I'll be able to get my C. After getting C, that was, let me see, Roman 1. Roman 1, they wanted the capacitance of the capacitor, so that's what they wanted. Then Roman 2, energy stored in the capacitor. Energy stored, we first code the formula, then we substitute. We already got the C, so come and substitute for C and for V and use the calculator to come up with the energy stored. Energy stored is measured in joules. Then question 2 came from UNEB 2013, paper 2, question 9c, and says a capacitor of capacitance C is fully charged from 200 volt from a 200 volt battery. It is then discharged through a small coil of wire embedded in thermally insulated block of heat capacity 250 joules per Kelvin. If the temperature of the block rises by 0.4 Kelvin, calculate the value of C. So here we shall know that energy stored will be equal to the heat dissipated in the coil during discharge. Therefore, formula for energy stored in a capacitor is given by a half CV squared. And the heat dissipated, here we shall use heat capacity, because in the question gave you joules per Kelvin, that is heat capacity. If it was joules per kilogram per Kelvin, that would be specific heat capacity. But now because it is heat capacity, we are using C times change in temperature, which is that. Therefore, we shall come and substitute a half. C we don't know is the one we are looking for, then V we know it, heat capacity we know, and change in temperature we know it. So I think we realize that we have only one unknown, so our aim is to simplify and make C the subject, and that will be the answer they wanted. Then question 3 came from UNEB 2006, paper 2, question 10C, and says the capacitance of a variable radio capacitor can be charged continuously from 10 picofarad up to 900 picofarad by turning the dial from 0 degrees to 140 degrees. With the dial set at 140 degrees, the capacitance is connected to a 9-volt battery. After charging, the capacitor is disconnected from the battery and the dial is turned to 0 degrees. Calculate Roman 1, the charge on the capacitor. Roman 2, the energy stored in the capacitor with the dial set at 140 degrees. And Roman 3, the work required to turn the dial from 140 degrees to 0 degrees if friction is neglected. So we shall start with Roman 1, the charge on the capacitor. So we shall come as that with the dial set at 140 degrees, capacitance is 900 picofarad. But remember, we have to convert to farad by multiplying by 10 to the power negative 12. And the PD was 9 volt. That's what they told us. Therefore, it implies that charge will be CV. Come and substitute for C and for V to come up with this charge which they wanted. That was Roman 1. What about Roman 2? Roman 2, they want the energy stored in the capacitor with the dial set at 140 degrees. So initial energy stored is be given by half CV squared. So when it is 140, we saw that when it is 140 degrees, capacitance is this. So that's what we substitute here. And V is this, so that's what we substitute there. And when you use the calculator, we shall come up with this as the answer. Then Roman 3, the work required to turn the dial from 140 degrees to 0 degrees if friction is neglected. So with the dial set at 0 degrees, the capacitor is disconnected from the battery. What does that mean? It implies the final energy will be given by Q squared over 2C. So the charge is this and the capacitance is that. I think that's why we already know this formula. There are two formulas we got for energy stored. So here we are using this. And the reason is because it was disconnected from the battery. That's why there is no V in this expression. So now use the calculator, I'll come up with this as the energy stored. But they want work done. So work done will be initial energy stored minus final energy stored. When I subtract the two, I'll be able to get the answer they wanted. So now we shall start our topic, capacitance of a charged sphere. So here we shall suppose a sphere of radius r situated in a medium of permittivity epsilon and is given a positive charge Q. The charge on the sphere gives rise to a potential on the outside surface of the sphere as if all the charges were concentrated at the center of the sphere. The surface of the sphere has a potential and the potential will be given by Q over 4 pi epsilon r. So we already saw this under electrostatics. That means that when I bring this one this side, I'll come up with, okay, when I try to rearrange, this is how I'm going to rearrange. I'll bring the whole of this this side and take this V this side, we shall see why. So when I do that, I'll come up with this, and here I'll come up with 2 over V. Now why do I want 2 over V? It is because 2 over V is equal to C, which they want here. Therefore, what I'm going to do, the whole of this will be replaced by C to come up with C equal to 4 pi epsilon R as my expression for capacitance of an isolated charged sphere. So if the sphere is in vacuum or air, the capacitance will be given by 4 pi epsilon naught R. So as long as you hear the word isolated charged sphere, just know that the formula for capacitance is C equal to 4 pi epsilon naught R. That is if it is vacuum. If it is not, you just use this. But for this part, we shall not be using any other permittivity. The permittivity we shall be using, it will be vacuum until we reach the last part, which has the word dielectrics. That's when we shall use other permittivities. So with that formula, let's go through these questions. So question 1 came from UNEB 2020, which is the last year. Paper 2, question 10, A Roman 2, and says, a conducting sphere of radius 7.5 centimeters is maintained at an electric potential of 9 kilovolt. Calculate the charge on the sphere. So this question, there are 2 ways to answer it. The first one is using the approach we have just seen, that capacitance is equal to 4 pi epsilon naught R. So 4 pi is there, epsilon naught is a constant, then R is given, so we have to convert to meters. When you do that, you'll come up with this capacitance. But the question wants charge. So when I get capacitance and I also know the PD, I can easily get the charge, which is Q equal to CV. So C is there and V is there, you'll be able to get the charge they wanted. That is if you use the knowledge you have just seen. But also, you can use the knowledge in the previous video, and you'll see that potential, it will be equal to K Q over R, where K is 1 over 4 pi epsilon naught. So come and substitute for V, substitute for K. K is a constant, we saw it under electrostatics. R is this. Therefore, when I make Q the subject, Q will be equal to this. So both are correct. Any of the 2 methods is okay. That was question 1. What about question 2? Question 2 came from UNEB 1995, paper 2, question 9A, and says, a conducting sphere of radius 9 centimeters is maintained at an electric potential of 10 kilovolt. Calculate the charge on the sphere. So this is in the same format as we have seen in question 1, so we shall use both methods. Method 1 is by first getting capacitance 4 pi epsilon naught R to come up with the capacitance. Then you can get the charge CV, so C times V, to come up with the charge they wanted. Alternatively, you can first say that V is equal to KQ over R. Then you substitute for V, for K, and for R to remain with Q as the only unknown. Then when you make Q the subject, that will be the answer they wanted. So any of the 2 methods is okay. Then question 3 came from UNEB 2002, paper 2, question 10C, and it says, a hollow spherical conductor of diameter 21.4 centimeters carrying a charge of this is raised to a potential of this. Find the permittivity of the surrounding medium. So here the permittivity, so what you shall do, first get capacitance because you know the charge and you also know the potential. So we can divide to get the C, which is this. Then from there we shall say, what is the radius? Radius will be, because they told you diameter is this, therefore radius will be half of that. But it has to be converted to meters. That's why you multiply by 10 to the power negative 2 to give you this as the radius. Then from there, remember that C is equal to 4 pi epsilon r. Therefore, when I substitute by making epsilon the subject, I'll come up with C over 4 pi r. So C is there, 4 pi is there, and r is there. Then use a calculator to come up with this as the permittivity of the surrounding medium. Alternatively, you can first get the radius in meters. Then from there we'll see that V is equal to Q over 4 pi epsilon r. So this should be small r. I can edit that. Then we'll come and substitute. So make epsilon the subject, will give you Q over 4 pi r V. So substitute for Q, 4 pi r, and for V. You'll be able to get the answer when you use the calculator, and that will be the answer that you wanted. So we shall start our topic, arrangement of capacitors in circuits. So there are two types of arrangement of capacitors in circuits, and that will be series arrangement and parallel arrangement. So capacitors can be arranged in series or in parallel. We shall see what each means. So let's start with series arrangement of capacitors. So what we are going to do, we are going to first derive a formula which can be used to get the effective capacitance of capacitors arranged in series. So we shall consider three capacitances C1, C2, and C3 connected in series across a battery as shown below. So we shall need an illustration. So those are the capacitors. Now, because of this PD, there will be charge on each of these capacitors and also a PD for each. So this PD V1 is the one across this capacitor, V2 is the one across this capacitor, and V3 is the one across this capacitor. Then because of the polarity of this dry cell or battery, this is a positive, negative polarity, meaning that this part will be positively charged and this one will be negatively charged. Positively charged, negatively charged. Positively charged, negatively charged. So what you should realize is that all the capacitors have the same magnitude of charge. That is one. Then two, you realize that the PD across each capacitor is different. For this one is V1, for this one is V2, and for this one is V3. So whenever two capacitors are in series, just know charge will be the same and PD will be different. So that's what I've told you. Capacitors in series have the same charge. And total PD, because PD is different, total PD will be the sum of all the individual PDs. Therefore, total PDV is equal to V1 plus V2 plus V3. But we know that V is equal to Q over C. We have already seen this formula. V1 is equal to Q over C, C1. V2 will be Q over C2. And V3 will be Q over C3. So it should have been Q3, but because the charge is the same, that's why we put the same letter, Q throughout. If it was different, we would have used Q1 here, we would have used Q2 here, and we would have used Q3 here. But because it's the same, we shall use the same figure, the same symbol. Then from there, what I'm going to do, I'll substitute for V1, V2, and V3. Then I'll realize that 2 is common. I can factorize it out to remain with 1 over C1, 1 over C2, and 1 over C3. Then from there, I'm going to bring this 2 this side to come up with 2 over V. Therefore, I'll come and say that if C is the effective capacitance of the system, it implies that C is equal to 2 over V. But we already have here V over 2, meaning that if 2 over V is C, then V over 2 will be the reciprocal, which is 1 over C. So this is what we use to get the effective capacitance of capacitors in series, in case there are 3 or more. But if there are 2, there is a special, it will be regarded as a special case. So in summary, when capacitors are connected in series, one charge on each capacitor is the same, and total charge is equal to the charge on any one of the individual capacitors. This is just a summary. Then the effective capacitance is less than the least individual capacitance. So the effective one, or the total, must be less than the smallest of those capacitors in series. Then 3 is that PD across capacitors is inversely proportional to their capacitances. We have already seen that V is 2 over C, meaning that they are inversely proportional. Then total PD is the sum of the individual PD. So that is the summary. Then, like I told you, there's a special case if there are 2 capacitors in series. So if 2 capacitors of capacitances C1 and C2 are connected in series across a battery, the effective capacitance C of the system can be got as follows. So still we use the same formula. 1 over C is equal to 1 over C1 plus 1 over C2. And when we get the LCM of this, it will be C1, C2. Now C1, C2 divided by C1, you get C2 times 1 to give you this C2. Then C1, C2 divided by C2, you get C1 times 1 to get C1, which is this. Then from there, when I get the reciprocal, here it will be C over 1, and here it will be product over sum. So this is the way we can get capacitance of 2 capacitors in series. The numerator will be a product, and the denominator will be a sum. Now that was series. Now what about parallel arrangement? So still we need to derive a formula which can be used to get the capacitance of capacitors connected in parallel. So consider 3 capacitors of capacitances C1, C2, and C3 connected in parallel across a battery as shown below. So we need an illustration. So those are the capacitances in parallel, and this is the PD across them. So in this case, you realize that the charge is different on each capacitance, on each capacitor. So here the charge divides. So here the charge is 2 at this point, but when it reaches here, it has to split. One is this, goes this side, another on this side, another on this side. So this will be the motion of direction of current, and this will be the direction of charge. So the charge will move in this direction, and when it reaches here, it will split, one this side, one this side, and one this side. So that is why we see here Q1, Q2, and Q3. So that is what you should remember. Under series, the charge was the same, but when it comes to parallel, the charge will be different. 2, under series, the PD was different, but when it comes to parallel, PD will be the same. So here we shall come as that PD across each capacitance in parallel is the same, but the charges on each capacitor are different. Therefore, total charge is given by adding all the three. So Q is equal to Q1 plus Q2 plus Q3. But we know that Q is equal to CV, therefore Q1 is equal to C1 plus Q1 times V, Q2 is equal to C2 times V, and Q3 is equal to C3 times V. Therefore, I'll come and substitute for Q1, Q2, and Q3. Here I realize that V is common, so I'll pull it out and divide throughout by V to come up with Q over V equal to C1 plus C2 plus C3. Then if C is the effective capacitance, effective means total, it implies that C is equal to Q over V. And when I substitute this Q over V, I'll come and replace it with C to come up with C equal to C1 plus C2 plus C3. So what does that mean? It means that when capacitors are in series, the effective capacitance is got by adding all the three, all the capacitors. But when they're in parallel, it is different. For example, if there are two capacitors in parallel, sorry, in series, it will be got by product over sum. But if there are more than two, you have to use the reciprocal, as we have already seen. So shall I make a summary that if capacitors are connected in parallel, it implies that the PD applied across each capacitor, PD is applied across each capacitor and it will be the same. Then the total charge is equal to the sum of the individual charges. Then the effective capacitance is the sum of the individual capacitances. So with those two formulae of series and parallel, we can go through these questions. So question 1 came from UNEB 2014 paper 2 question 10D and says a capacitor X of 5 microfarad and another capacitor Y of 8 microfarad are connected in series with a 20-volt supply. Calculate Roman 1 the charge on X and Roman 2 the potential drop across X. So here I shall need to make a simple sketch to illustrate the question. So you have this capacitance X and this capacitor Y with capacitance 8 microfarad. And this is the PD applied. So they are connected in series. So one shall say that total capacitance is equal to, because there are two capacitors in series, the effective will be got by product over sum. So product of these two is here and sum of these two will be denominator. When we use the calculator, we shall come up with this, and the unit is microfarad because these ones were in microfarad. Then total charge, remember when they're in series, the charge is the same, therefore total charge will be equal to total capacitance multiplied by the total PD, which is this, to give you this as the total charge they wanted. Therefore, because the charge is the same, it implies that the charge on X will be this. So if they had asked for charge on Y, we would also get this same value. So now shall go to Roman 2. Roman 2, they want the potential drop across X. In other words, the PD across X. So PD, the good thing, we know the charge on this capacitor and also we know its capacitance. Therefore, we can easily get the PD by saying Vx is equal to Q over Cx. So the charge is Q and the capacitance is Cx. That's why you are using Q over Cx. So our Q is this and our capacitance is this, but we have to convert to farad. Then in the end we shall come up with this as the PD they wanted. So that was question 1. Now we shall go to question 2, which came from UNEB 2010 paper 2 question 10C, and says 3 capacitors of capacitances, these ones, are connected as shown in figure above. Calculate the energy stored in the 2 microfarad capacitor when fully charged. So this is the circuit they are giving us, and previously we had already looked at the formula for energy stored in a capacitor. So shall use that formula to come up with a solution for this question. So first is to get the effective capacitance. So we are going to combine capacitors 0.7 and 0.3 in parallel. So I think we realize that these ones are in parallel because if charge flows up to here, it has to divide one this side and one this side. Now because charge is different, it implies that these two are in parallel. So we are going to first combine them to get one capacitance in parallel. So when I combine, because they're in parallel, you shall just add. So this plus this to give you 1 microfarad. So after combining, the circuit will become like this. So here there were 2, but now it is 1 capacitance. Then in that circuit, you realize that now these ones are in series because the charge which reaches here is the same charge which reaches there. So they are in series. And because there are 2 capacitances in series, we shall use the special case of product over sum. Therefore, combining this and this in series, capacitance will be product over sum to give you this microfarad. Therefore, total charge on C2. Now, in this case, it implies that we have got the charge on C2, which is the total capacitance, and we also know the total PD, meaning we can get the total charge. So total charge is equal to total capacitance times total PD, which is this, to give you that as the charge. And that total charge is the charge on each capacitor because they are in series. Therefore, energy stored in the 2 microfarad capacitor. So when you look at this 2 microfarad, capacitor, we have got the charge at this, and also we know this capacitance, meaning we can get the energy stored. So the charge with the formula is Q squared over 2C. I believe you already know this formula. So Q is this and C is this, which is here, but you convert to farad. In the end, you come up with this as the charge, as the energy they wanted. So that was question 2. Now we shall go to question 3, which came from UNEB 2016 paper 2 question 10B, and says a network of capacitors of capacitances, these ones, is connected to a battery of 9 volt as shown in figure below. So this is the circuit. Calculate Roman 1 the charge stored on the 50 microfarad capacitor. So the charge stored on this. And Roman 2 the energy stored in the 40 microfarad capacitor. So they want this charge. So this, because of this polarity, charge flows in this direction, and when it reaches here, it will have to divide one this side and one this side. What does that mean? It means that these 2 capacitors, this and this, are in parallel. So let's first combine those 2 capacitors in parallel. So when you combine this and this in parallel, we shall just add to give you 120 microfarad. So when we combine, the circuit will now become this. We have combined these ones into one capacitance. Now, after combining, you realize that because of this polarity, the same charge here will be the same charge at this capacitor. Therefore, these two capacitances are in series. Because they are in series and they are two, we shall use the special case, which is product over sum. So the capacitance will be product over sum to give you 30 microfarad. So we now know the total capacitance and we know the total PD, meaning we can get the total charge. So total charge will be total capacitance times total PD, substitute. Now this was in microfarad, that's why we convert to farad by multiplying by 10 power negative 6. And then we shall get the charge in coulomb. After getting the total charge, we shall go back to the question. The question wants the charge stored on the 50 microfarad. So they want the charge at this point. Now the good thing, we already know the capacitance, but we don't know the PD. And we also don't know the charge which they want. Therefore, we have to first get the PD across this capacitance. So the PD across the parallel combination, so the PD across the 50 microfarad is the same PD across this because they are in parallel. So PD across that, we shall come and say it will be total charge over the capacitance for the parallel combination, which we got here, to give you the PD across the parallel combination as that. So now that means that the PD across this is 2.25, also the PD across this is 2.25. So now that we have got the PD here and also the capacitance, we can get the charge. Therefore, charge on the 50 microfarad will be C times V. So C will be the capacitance, which is this, and V will be the PD across that capacitance, which is that. So you come and substitute and get the answer they wanted. So now shall go to Roman 2. So Roman 2, they want the energy stored in the 40 microfarad capacitor. So 40 microfarad, we know this will be the capacitance, and we also know the total charge. That will be the charge across that capacitance. Therefore, now that we know the capacitance and the charge, we can easily get the energy stored. So you come and say that energy stored is given by that formula. Therefore, you shall substitute for Q, which is the total charge, and we got it here. Then the capacitance, which is the 40 microfarad, we convert to farad. And use the calculator, we shall come up with this as the energy stored. And that's what they wanted. So that was question 3. Now we shall go to question 4, which came from UNEB 2015 paper 2 question 9D, and says a 3 microfarad capacitor is connected in series with a 6 microfarad capacitor. The combination is then connected in parallel with 1 microfarad capacitor to a 12 volt battery as shown below. Calculate Roman 1 the charge stored by each capacitor, and Roman 2 the energy stored in the 6 microfarad capacitor when fully charged. So here they have helped us by specifying which ones are in series. So they have told us these are in series, and after that the combination is in parallel with this. So parallel, what does it mean? It means that parallel PD is the same. So the PD across this is 12 volt, and the PD across this combination is also 12 volt. So for this 1 microfarad, we have the capacitance and the PD, meaning you can get the charge straight away. So let's first do that. So So you come out that the charge on 1 microfarad is equal to the capacitance, which is 1 microfarad, and the PD across that 1 microfarad, which is 12, to give you this as the charge. For these other two, we have to first combine them. So when I combine these ones series, I'll use the method of product over sum to give you 2 microfarad. So when I combine the two, I'm going to come up with this. So that means that now these two are in parallel, meaning this PD across this, we already seen it is 12, and also PD across C1 is also 12. Therefore, now that I know the PD across this C1 and also the capacitance C1, I can get the charge at this combination, series combination. So the charge on the series combination will be C1 times V, which gives you 2.4 x to 5 coulomb. That means that because they're in series, they have the same charge. Therefore, the charge on each of this and this will be this 2.4 x to 5. That is Roman 1. What about Roman 2? Roman 2, they want the energy stored in the 6 microfarad capacitor when fully charged. So they want this. So the good thing, we know the capacitance and also the charge. So you come as that energy stored will be Q squared over 2C. So the charge is that and the capacitance is that. You come up with this as the energy stored. So that was question 4. Now we shall go to question 5. Question 5 came from UNEB of November 1998, paper 2, question 10C. This is the circuit, and it said the figure above shows a network of capacitors connected to a DC supply of 120 volt, which is this. Calculate Roman 1, the charge on the 4 microfarad capacitor, and Roman 2, the energy stored in the 1 microfarad capacitor. So they want the charge on this. First of all, if this charge, the charge from here goes through this, and when it reaches here, it has to divide into 2. Meaning, to get this charge, we need to get the PD across this capacitor. And from there, it goes up to this. So the first thing to do is to combine these two capacitors in parallel. So combining 1 microfarad and 4 microfarad in parallel, I'll come up with this. I have to add the 2 to give you this. So when that happens, the circuit will now become this. So all these three are in series. Therefore, I have to get the effective capacitance in series. Because they are 3 and not 2, we shall use the reciprocal. So combining all those ones in series, we shall use the reciprocal. 1 over C2 is equal to 1 over 5 plus 1 over 2 plus 1 over 2. Therefore, when I use the calculator, this one will give me 6 over 5. Therefore, C2 will be this. So that C2 is the total capacitance. Now that I have the total capacitance and also the total PD, I can get the total charge. So total charge will be total capacitance times total PD to give you this. And now that I know the total charge, it implies that I can get the total, I can get the PD across the parallel combination. Because if you look at this parallel combination, the charge through across this, the charge through this will be the total charge, because the one which comes from here goes through here, goes through there, and also goes through there. So the charge of at this part is the total charge, and I also know the total and I also know the capacitance for parallel. Therefore, I can easily get the PD across the parallel combination, and it will be this. So now that I've got the PD, if I go back here, I now know the PD across this, and I also know the capacitance, meaning I can get the charge at that 4 microfarad. Therefore, the charge on the 4 microfarad will be the capacitance, which is 4 microfarad, and the PD, which is this, to give you this as the charge. So that was Roman 1. What about Roman 2? So Roman 2, they want the energy stored in the 1 microfarad capacitor, energy stored in this. So the good thing, I know the PD and I also know the capacitance. Therefore, energy stored will be a half CV squared. So come and substitute for C and for V to give you that as the energy stored. Then question 6 came from UNEB 2018 paper 2 question 10D and says a battery of EMF 120 volt is connected to a network of capacitors as shown in figure 6. So this is the circuit. Calculate Roman 1 the charge on C1 and Roman 2 the energy stored in C5. So in this case, charge will flow from here, goes here, it will split this side and this side. So the one here will come up to here and here, then the one this side will come here and split again, this side and this side. Here it will combine to go through this, and after that it will combine to go back to through C1 and back to the source. So what does that mean? So in order to get the effective capacitance, you have to first get where it last divided. So it is this part. So these two, we are going to first get the capacitance of these two combined parallel capacitors. So let's do that. So we shall come and say that combining C3 and C4 in parallel, we shall come up with that. So parallel we just add. Now when we get this, now the circuit will look in this way, because we have combined the two capacitances which were in parallel at this part. So that means that now next is to combine these two. Why are we combining the two? Because remember this charge last divided here, and from here this went through this to come here at this junction, and this one went through these two to come back at this junction. So that means that we have to first combine these two, which will be in parallel with this. So when I combine C2 and C6 in series, I'll come up with this. So combining those in series I have to use product over sum to give you 2 microfarad. So when I combine the two, now the outcome will now be this. Remember, here there are two capacitances, but now we have combined them into one. Now that you have combined them into one, you realize that this and this are in parallel, because at this point charge will divide or split. Therefore, the next thing to do is combine these two which are in parallel. So let's do that. So parallel, just add to give you 3 microfarad. Now when they combine those two in parallel, the circuit will now become this. I think we realize that it is now simpler. So these diagrams are a side work. That is why they are not part of the main content. And that means that you don't need to draw them if you can easily internalize them in the head. So now these are the two remaining capacitances in series. Therefore, you can combine the two using product over sum to get the total capacitance. So when I combine, I'll come up with this product over sum, which gives you 2 microfarad. So now that I know the total capacitance and the total charge, and the total PD, I can get the total charge, and that total charge will be the charge on C1. If you look at this, the total charge you are going to get will go through this and this, so it will be the same charge on C1. So charge on C1 will be total charge and total PD and total capacitance. Total capacitance is this, and total PD, you already know it. It is 120, so it gives you this as a charge on C1. So that was Roman 1. What about Roman 2? For Roman 2, they want the energy stored in C5. Energy stored in this C5. So I know the capacitance, but I don't know the charge, and I also don't know the PD. So I have to get one of those. So the PD across C1, if you look at this, the PD across C1 will be equal to the charge over the capacitance, because I already know the charge, which is this, and I know the capacitance across the capacitance of C1. I can get the PD across C1, which is 40 volt. So now that I know the PD across C1, I can easily get the PD across C8 by subtraction. So PD across C8, now here they've called this PD across C5. Why? Because if you look at this, the whole of this and this are in parallel, meaning the PD will be the same, and the whole of all these ones is what we call the C8. If you are following, the whole of that is C8. So PD across C8 is the same PD across C5, because they are in, these two branches are in parallel, and the effective capacitance in parallel was C8. So PD across C5 will be good by subtraction to give you 80 volt. So now that I know the PD, I can easily get the energy stored in C5. I have CV squared to give you this as the answer they wanted. So now we shall go to question 7, which came from UNEB 2008, paper 2, question 10C, and says, the figure above shows a network of capacitors connected to a 10 volt battery. Calculate the total energy stored in the network. So total energy stored means you have to first get the total capacitance. So the capacitors are many, but it will not be that hard, because charge flows from here. When it reaches here, it splits. One goes this side and one goes this side. The one which goes here splits again. One goes this side and one goes this side. Then it combines to come here. Similarly, the one which went here splits. One goes this side and one goes this side. Then the one which goes this side passes through this to reach here, and also this passes through this to reach here. This junction they combine to come through this, and at this junction they combine with this one to come through this. Then they go back to the source. Now what does that mean? It means that these two are in parallel. Then these two are in series. Then when you combine this in series and this one, these two will be in parallel. Okay, so it may be complicated if we combine all those ones, but what we are going to do, we are going to be breaking it down as we have been doing in the previous questions. So let's start by combining the 8 microfarad capacitors which are in series. So remember we said these ones, are in series. So we are going to combine them into one. So series, it will be product over sum to give you 4 microfarads. So what does that mean? It means that now these which were 2 have now been reduced into 1 capacitance, which is 4 microfarad. Then we are going to combine C1 and the 2 microfarad which are in parallel. Now here, if you look at this and this are in parallel. So what we are going to do, we are going to combine them into 1. So when you combine, you shall come up with 6 microfarad. And after combining, this is what will happen. So if you look at this previously, these were 2, but now we are combining them into 1 to give you this C2. After that, we are going to combine now C2 and the 4 microfarad in series. So this is C2 and this. So here we have this and this which are in series. When you combine them, we shall come up with C3, which is, so series, which is product over sum to give you 2.4 microfarad. So when I combine those two, it means I'll come up with a capacitance which is now 1. There were 2 these ones, but now we have combined them to give you 1 capacitance, which is that. Okay. So next we are going to combine the 6 microfarad capacitances in parallel. So we are going to combine these ones, these 2 which are in parallel. When you combine, you shall add them to come up with 12 microfarad. So that means that now these 2 have been combined in to give you 1 capacitance, which is this. Then from there you will realize that these 2 are also in series. Therefore, we are going to combine the 2 which are in series by product over sum to give you 2.4 microfarad. So that means that the circuit now becomes this. So initially there were these 2, now we have combined them into 1 to give you this. I think we'll see that the circuit is now going on reducing and reducing. It is no longer complicated. So now what we have this and this which are in parallel, because at this point the charge divides. So when they combine those in parallel, we shall just add to give you 4.8 microfarad. So that means that now these 2 have been combined into 1 to give you this. So now I think I'll say that is now simpler because these 2 are now in series, meaning you can get the total capacitance. So combining this and this in series, we can get the total capacitance as that. So now that we know the total capacitance and we know the total PD, we can get the total energy from a half CV squared, and to give you this, and that will be the energy they wanted. So now we shall start our topic, joining 2 capacitors in a circuit. So when 2 capacitors are joined together, charge flows until the PD across the 2 capacitors is the same. So charge will flow until the PD is the same. And as this charge is flowing, it will generate some heat, and that heat will cater for the loss of energy. So that's why we are saying that loss of energy occurs when the capacitors are connected together, and this is due to the production of heat when charge flows in the wires connecting the two capacitors when they are joined. So as this charge flows, heat is generated, and that heat generated accounts for the loss of energy. That means energy before connection will be different from energy after connection. So shall need an illustration. So here what it means is that you'll have a capacitor C1 of capacitance C1 which is charged to a PD V1. After charging it, you will connect it to an uncharged capacitor of capacitance C2 and in parallel. When they are connected in parallel, charge will flow until the PD is the same in both capacitances. So this one and this one, they all have a PD V2, and that means that here now the charge will reduce to Q1, and so that this one also acquires a charge Q2. Now because the charge at Q2, it has flown from this capacitance of C1 up to this, it implies that when you combine these two, you'll have to get back the original charge. So this charge is equal to this plus this, because initially it was Q, then it reduced in order to charge this other capacitance. So that what we need to know is that total charge before connection is equal to total charge after connection. Then you need to know that the PD after connecting, the PD is the same across both capacitors because it is a parallel arrangement. So the following can be concluded. 1. Total charge before connection is equal to total charge after connection. Then 2. PD across both capacitors is the same after connection, and to be this V2. Then 3 is that the capacitors are arranged in parallel. So with that, we can go through these questions. Question 1 came from UNEB 2002, paper 2, question 10D, Roman 2, and says a 20 microfarad capacitor is charged to 40 volt and then connected across an uncharged 60 microfarad capacitor. Calculate the potential difference across the 60 microfarad capacitor. So if we are to illustrate, first we have a capacitor of 20 microfarad which is charged to 40 volt. Then from there you connect it to a 60 microfarad uncharged capacitor. When that happens, the PD will come reduced to a PD V2, which we don't know yet. But what we know is that the PD will be the same in both capacitances. And 2, we know that the total charge before connection will be equal to total charge after connection. Therefore, we shall come and remember that total charge before connection is equal to total charge after connection. So total charge before connection, we know the total capacitance and also the total PD, so that's why we have here C1 V1. Then here we need to get the total capacitance because they are in parallel. Total capacitance will be got by adding the 2 to give you this. Then the total PD after connection will be this V2, which we don't know yet, and it is here. Then from there we are going to substitute. So substitute for C1, convert to farad, it was microfarad, you convert to farad, V1, which is this, then C1, C2, and V2. Now V2 is the only unknown, meaning we have to simplify and make V2 the subject. So when that happens, V2 will be 10 volt. So that is what they wanted, because they said calculate the potential difference across the 60 microfarad capacitor. So because they're in parallel, PD will be the same, and that's what they wanted. Then question 2 came from UNEB 2019, paper 2, question 10C, and says a 60 microfarad capacitor is charged from a 120 volt supply. It is then connected across the terminals of a 20 microfarad capacitor. Calculate Roman 1, the final PD across the combination, and Roman 2, the difference in the initial and final energy stored in the capacitors, and comment on the differences. So first we can illustrate that is before connection, then after connection it will be this. So the PD across the after connection is one they want, and that will be V2. So we shall still follow the same procedure. Total charge before is equal to total charge after. Then we quote the formula for total charge before and also total charge after and equate the two. Then we substitute. After substituting, V2 is the only unknown, so you have to simplify and then make V2 the subject. And that's what they wanted for Roman 1. Then Roman 2, they want the difference in the initial and final energy stored in the capacitors. So they want total energy before connection and total energy after connection. The good thing for each we have C and V, meaning we can use a half CV squared. So total energy before connection, we shall use a half C1 V1 squared. So substitute for C1 and for V1 squared to give you this as the energy before. What about after connection? After connection, still we shall use a half CV. So this will be the total capacitance and the PD, total capacitance, PD, to give you this. Then they said you get the difference in energy. So difference in energy will be got by subtracting the 2 to give you this. And after that, they told you to account for the difference, to comment on the difference. So you shall come and say that the final energy stored is less than the initial energy. And this is because some energy is lost as heat in the connecting wires when the capacitors are joined together. I think that's what we already explained at the starting part. Then question 3 came from UNEB 2011 paper 2, question 10C, Roman 2 and Roman 3. It says a 10 microfarad charged capacitor, a 10 microfarad charged to 200 volt is connected across an uncharged 50 microfarad capacitor. Calculate the total energy stored in both capacitors before and after connection. Then account for the difference in the energies calculated in Roman 1. So still we shall follow the same procedure. We shall illustrate. That is before connection, then after connection. Then we shall remember that total charge before connection is equal to total charge after connection. Then we quote the formula, substitute, simplify, and get the PD they wanted. So they wanted the total energy before connection, which is that. So quote the formula, substitute, and use a calculator. What about after connection? So quote the formula, substitute, and then use a calculator. Then they wanted you to account for the difference. So we shall come and say that the difference in the total energy stored in both capacitors before and after is due to the energy lost as heat in the connecting wires when capacitors are joined. As simple as that. Then question 4 came from UNEB 1996 paper 2, question 9b, and says a 60 microfarad capacitor is charged from a 100 volt supply. It It is then connected across the terminals of a 15 microfarad uncharged capacitor. Calculate Roman 1, the final PD across the combination, and Roman 2, the difference in the initial and final energies stored in the capacitors, and comment on the difference. So the format of the questions will always be the same in this part. So still we shall follow the same procedure. First is to illustrate. That is before, then after we also illustrate. Then from there you shall remember that total charge before is equal to total charge after. Then we shall quote the formula, then substitute. After that we shall simplify and then get the PD they want. So the procedure is always the same. So that was Roman 1. Roman 2, they wanted the difference in the initial and final energy, and comment. So total energy before connection, quote the formula, substitute, use a calculator to give you this. Then also total energy after connection, quote the formula, substitute, use a calculator. Then the difference will be that, subtract to give you that. Then also comment. So comment will always be the same. Final energy stored is less than the initial energy, and this is because some heat is lost, some energy is lost as heat in the connecting wires when the capacitors are joined. So now we can start our topic, dielectrics in capacitors. So in simple terms, a dielectric is an insulator. So they are the dielectrics in capacitors, they are used to separate the plates of the capacitor and to reduce the chances of electric breakdown when a large PD is applied. So previously we have seen capacitors are represented in this form, and this in between the plates was air or free space or vacuum. But now in this case we shall need to put what we call an insulator or a dielectric and the reason is to reduce chances of electric breakdown when a large PD is applied. And also another advantage is to separate the plates. But more of the advantages are found in the notes of physics paper 2 in that book. So when they talk about a dielectric, this is what they mean. A dielectric material is placed in between the capacitor plates, and dielectric in simple terms is an insulator. So you can define it as a material which has no conductible charges. It must be an insulator and is able to withstand high electric fields before it breaks down. And the reason is because of this, because its one purpose is to reduce electric breakdown. So it must be able to withstand high electric fields before it breaks down. Some of the examples can be glass, polythene, fur, wool, etc. As long as it's an insulator and it's able to withstand high electric fields, it is okay. So there are some terms which we also need to know. One is dielectric strength. So what is a dielectric strength? So dielectric strength of an insulator or a substance is the potential gradient. Now when we talk about potential gradient, talk about the value of electric field intensity. You can say potential gradient or electric field intensity because potential gradient is V over D, And you already know, we already saw under electric field intensity between two parallel plates that V over D is equal to electric field intensity. So when they talk about potential gradient, just know they mean electric field intensity because they are the same. Is the potential gradient beyond which a dielectric breaks down. And this value varies for different substances. So that is what we call dielectric strength. Then what about dielectric constant? So another word for dielectric constant is relative permittivity, and is denoted by a symbol epsilon r. Remember, permittivity of free space was epsilon naught. Now relative permittivity is epsilon r. So this symbol will be used more frequently in the calculations of this video. Now, what is a dielectric constant, or what is relative permittivity? So you can answer that this is the ratio of the capacitance of a capacitor when the space between its plates is filled with a material, to capacitance of the same capacitor when the space between them is filled with a vacuum. So you get a capacitor, then you put a material between them. So this material affects the capacitance of the capacitor. So you get its capacitance. So it can be C1. Then you also get the capacitance when the material, when there's no dielectric and it is free space. So you get also its capacitance. So you get their ratio, and that will be equal to the relative permittivity. So we shall come here and say that if V is the PD across the plates of a capacitor when the space between them is filled with a material, and V naught is the PD across the capacitor plates of the same capacitor when the space between them is vacuum, it implies that C is equal to Q over V and C naught is equal to Q over V naught. So the charge will be the same. It is the PD which is changing. So C is the capacitance when there is a dielectric. C naught is the capacitance when there is no dielectric. Therefore, relative permittivity from the definition it will be C over C naught. And when I substitute for C and for C naught, I'll come up with V naught over V. So these are the two formulas for relative permittivity. One is this one, and we have already seen the definition. Another one is in terms of PD. So that means that you can also define relative permittivity in terms of PD. But remember, previous for capacitance, it was capacitance when the place is filled with dielectric over capacitance when the space is vacuum. But when it comes to PD, it is PD when the space is filled with vacuum over PD when the space is filled with a dielectric. For example, let's see this definition. So dielectric constant can also be defined as the ratio of PD across the plates of a capacitor when the space between them is vacuum. So here I first talk about vacuum. I think you know the difference. For capacitance, we first talked about the material, then we went to vacuum. But here we have to talk about the vacuum followed by the material. So you can continue and say to PD across the plates of a capacitor when the space between them is filled with a material. That is when you're defining in terms of PD. But if you're defining in terms of capacitance, you should remember to first talk about the material, then followed by a vacuum. So the order is very vital. Also, there's this definition which we also saw about capacitance, that capacitance is equal to permittivity over material times area of the plates divided by the plate separation. Therefore, this will be for when there is material, and this when there is no material, when the space is filled with vacuum. Here it will be epsilon naught. So epsilon naught means permittivity of free space times area of the plates divided by the separation of the plates. Now, when we also divide the two, we shall come up with something. So substitute for this and also substitute for this. You realize that this one cancels, and remain with this divided by this, which is here. So that gives us a third definition of relative permittivity. So relative permittivity, or dielectric constant, like I told you they are same, can also be defined as the ratio of the permittivity of a material to permittivity of free space. So it has to be material first, followed by free space. I think this is more friendly because it is brief. So any of the three definitions is okay, though personally I would prefer this one, which is a little brief. So that means that when I try to make this permittivity of material subject, it will be relative permittivity multiplied by the permittivity of free space. So why do I do that? It is because most times we'll be given relative permittivity, and this permittivity of free space is a constant, meaning that when you're given relative permittivity, it is possible to get the permittivity of a material. So you have to note that capacitance over capacitor when the medium is dielectric is given by this. This is what I told you, because when they give you relative permittivity, it implies that you can get the permittivity of that medium by multiplying relative permittivity by the permittivity of free space. So with that, we can go through these questions. So question 1 came from UNEB 2019 paper 2 question 10b Roman 2 and says a parallel plate capacitor is charged to 100 volt and then isolated. When a sheet of dielectric is inserted between the plates, the PD decreased to 30 volt. Calculate the dielectric constant of the dielectric. So this is PD when the plates are filled with vacuum, and PD when the plates are filled with a dielectric. Therefore, we shall come and remember that the definition of relative permittivity when the plates are filled with relative permittivity in terms of PD is PD when the plates are filled with vacuum over PD when the plates are filled with a material. Therefore, we shall come and put PD when the plates are filled with vacuum over PD when the plates are filled with the material to give you this as the relative permittivity they wanted. So that is question 1. Question 2 came from UNEB 2017 paper 2 question 10b and says a parallel plate capacitor with plate area this and plate separation this, so this is A, this is D, is connected to a 500 volt supply. Roman 1. Calculate the energy stored in the capacitor. And Roman 2. If the space between the plates is completely filled with oil and the total charge in the capacitor becomes this, find the dielectric constant of the oil. So that is when there is no dielectric, and this is when there is a dielectric. So Roman 1, capacitance at this stage, it is epsilon naught AD. So epsilon naught is a constant, area was given, and D was given. So come up with this as the capacitance when the plates are filled with vacuum. Therefore, energy stored is a half CV squared. So C is this we've got, and V they gave it to us, so we come up with this as the energy stored. Then part B, they say they put a dielectric. Let's see. So part B, they said if the space between the plates is completely filled with oil, that is the dielectric, and the total charge in the capacitor becomes this, find the dielectric constant of the oil. So you come and say that total charge is equal to total capacitance multiplied by total PD. So total capacitance is now epsilon r C 1, because we know that epsilon r is equal to capacitance when there is a dielectric over capacitance when there is vacuum. So when I bring this on this side, I'll come up with this capacitance as epsilon r multiplied by the capacitance when the plates are filled with vacuum. So this is where this one is coming from. Then from there I'll come and substitute. I know Q, R I don't know, epsilon R I don't know it, C1 I know it, and V2 I know it. Therefore my work is to make epsilon R the subject, and to be this, and that's what they wanted. Then question 3 came from UNEB 2003 paper 2 question 9b, and says an air capacitor of capacitance 400 microfarad is charged to 180 volt and then connected across an uncharged capacitor of capacitance 500 microfarad. Roman 1, find the energy stored in the 500 microfarad capacitor. And Roman 2, with the two capacitors still connected, a dielectric of dielectric constant this 1.5 is inserted between the plates of the 400 microfarad capacitor. If the separation between the plates remains the same, find the new PD across the two capacitors. So let's first start with Roman 1, which says find the energy stored in the 500 microfarad capacitor. So for Roman 1, we shall need a sketch for easy illustration. So initially it was this capacitor which was charged to this PD, then it was connected to an uncharged capacitor in parallel. That means that charge flows until PD is the same for both capacitors. Therefore, total charge before connection will be equal to total charge after connection. I believe you already saw this in the previous video. So before connection it will be this times this, which is here. Then after connection you shall first combine these two capacitances in parallel, which is this. Then you multiply by the total PD, which is that. Next is to substitute and make V and simplify. Then you make V2 the subject. So that will be the PD. Now that I've got PD, I can get the energy stored in the 500 microfarad. So it will be a half CV squared. C is that and V is that. So we come up with 1.6 joules as the energy stored. So that was Roman 1. What about Roman 2? Roman 2 says, with the two capacitors still connected, a dielectric of dielectric constant 1.5 is inserted between the plates of the 400 microfarad capacitor. If the separation between the plates remains the same, find the new PD across the capacitors. So here we shall come and make a sketch. First, before inserting the dielectric, we already saw that PD is 80 volt. Then what about after inserting a dielectric? So the new PD, we don't know it, so that's why you call it a question mark. Then here this capacitance now becomes epsilon r times the original capacitance without when the space is vacuum. So total charge before insertion is equal to total charge after insertion. So you come and substitute total capacitance before is this plus this, which is here, multiplied by V, PD. Then total charge after is this plus this, which is here, times the PD. So next is to substitute. Then I simplify, after which I'll make V3 the subject. And that's what they wanted. Then question 4 came from UNEB 1997 paper 2 question 10D and says a 2 microfarad capacitor can just withstand a PD of 5000 volts. That can just withstand a PD of 5000 volts uses a dielectric with a dielectric constant 6, which breaks down if the electric field strength in it exceeds this. Find Roman 1 the thickness of the dielectric, and Roman 2 the effective area of each plate, and Roman 3 the energy stored per unit volume of dielectric. So the hint is that capacitance is given by this. I think we already saw this formula, where A is the area, surface area, D is the separation, and epsilon r is the dielectric constant. So here they've helped us by giving us the formula. So just start with Roman 1, the thickness. So first of all, we know that E is equal to V over D, electric field intensity is equal to PD over separation. So come and substitute for electric field intensity and for PD to get their thickness or the separation. That was Roman 1. Then Roman 2, effective area of each plate. So you know that capacitance is given by that formula, so we shall come and make A the subject, then substitute, and then use a calculator to get the area they wanted. What about Roman 3? Roman 3, they want energy stored per unit volume of the dielectric. Energy per unit volume. So energy stored is half CV squared. Substitute for C and substitute for V to give you this. Then the volume is area, cross-section area times D, which gives you, so area is that and D is that, to give you this. Therefore, the energy stored per unit volume, we shall divide the two to give you this as the answer they wanted. Then question 5 came from UNEB 2012 paper 2 question 10C and says the diagram in the figure below shows an arrangement of 3 capacitors, these ones, of capacitances, these ones, respectively. So it's the diagram. Calculate the total energy stored, Roman 1, in all the capacitors when fully charged. Roman 2, when the space between the capacitors, between the plates of C2 is filled with a dielectric of dielectric constant 1.25. So we shall first start with this one, energy stored when the capacitors are fully charged. So first of all, we shall first combine the two capacitances C1 and C2 in series. So if you look at this, this and this are in series. These two capacitances are in series. So we are going to first combine the two by using the special case of product over sum. To come up with this. So when you do that, now the circuit becomes this. I think we realize these ones are now in parallel. So parallel we just add. So we shall combine the two capacitances in parallel to come up with the total capacitance, which is 7.6 microfarad. Therefore, I know total capacitance and I know total PD, so I can get total energy stored. So energy is a half CV squared. So substitute for C and substitute for V to come up with that total energy. So that was Roman 1. Now we shall go to Roman 2. Roman 2 says, when the space between the plates C2 is filled with a dielectric of dielectric constant 1.25, calculate the total energy. So here they are going to fill it with a dielectric. That means that now the circuit will become in this form. And because there is a dielectric, the capacitance will change. It is now relative permittivity times the capacitance when the space was vacuum. I think by now you know that formula. And when you do that, these two will still be in series. So you have to combine the two. So you come and say that new capacitance of C2 is C6, which is that, and after that we shall combine C6 and C1 in series by using product over sum to give you this. Then from there, when you combine, this is what will happen. We have C3 and C7, but they will be in parallel. So next is to combine C3 and C7 in parallel to get the total capacitance. After getting the total capacitance and we know the total PD, we can get total energy from half CV squared. So substitute for C and substitute for V to give you the energy they wanted. Then question 6 came from UNEB 2004 paper 2 question 9D, and it says, in figure above, C1, C2, C3 are capacitors or capacitances, these ones, respectively, connected to a battery of EMF 100 volt. Roman 1, calculate the energy stored in the system of capacitors if the space between the plates of C1 is filled with an insulator of dielectric constant 3 and the capacitors are fully charged. That is Roman 1. Roman 2, account for the change in the energy stored by an isolated charged capacitor when the plate separation is doubled. So let's start with Roman 1. So for Roman 1, new capacitance of C1, because there's a dielectric now, it becomes dielectric constant times the capacitance if it was vacuum, and to be 9 microfarad. So when I combine the capacitances C2 and C3 in parallel, so I'll come here and realize that these two are in parallel. This and this, they are in parallel, so I have to first combine the two. Therefore, I come and combine by adding them to give you 4 microfarad. And when I do that, I'll come up with this. So initially, this is what happened. We put a dielectric here and the new capacitor is now C4. And after that, after combining these two in parallel, we come up with this circuit. So this C4 and C5 are in series. Therefore, I'm going to combine the two capacitances in series by using the formula of product over sum to get the total capacitance as this. Therefore, total energy is equal to total capacitance multiplied by total PD to give you this as the total energy. That was Roman 1. What about Roman 2? Roman 2, they said, account for the change in the energy stored in an isolated charged capacitor when the plate separation is doubled. So here we need something like a derivation, so we shall say energy stored in an isolated charged capacitor is given by that. I have CV squared, where we can substitute for V to give you this other formula for energy. Also, we know that C is equal to epsilon naught AD for an isolated capacitor. Isolated means space between them is filled with a vacuum. So we are going to substitute for C to give you this, and in the end simplify to give you that. Now, since the whole of this is a constant, it implies that energy is proportional to the separation. What does that mean? It means that when the separation is doubled, energy stored is also doubled. And that's what they wanted. So this is just a note for you to easily understand this, that when the separation of the plates is increased, work is done in pulling the plates apart, and this work done is stored as electrical energy between the plates of the capacitor. So this one is just to help you to remember that when the separation increases, work is done and therefore energy also must increase. But the question wanted what happens when is doubled. So you had to go through this and you say when the separation is doubled, energy stored is doubled. Full stop. If they ask what happens when the separation is increased, this is what you would have written. Then question 7 says, question 7 came from UNEB 2000 paper 2 question 10b, and it says a capacitor filled with a dielectric is charged and then discharged through a milliammeter. The dielectric is then drawn halfway and the capacitor charged to the same voltage and discharged through the milliammeter again. Show that the relative permittivity epsilon r of the dielectric is given by this formula, where I and I prime are the readings of the milliammeter respectively. So here we shall need an illustration for you to easily make the derivation. So this is before you displace the dielectric. So when you connect this K to 1, you are charging it. And after that, when you want to discharge, you connect this switch K to 2. It will discharge through this milliammeter, and the ammeter will give a reading or a throw of I. That is before displacing. What about after displacing halfway? So what displacing halfway, still the circuit is like this. So when you connect this K to this, you're charging, and when you want to discharge, you connect this K to 2. It will discharge through this milliammeter and give the reading this. Now, when you displace halfway, there is something funny which happens. If you look at this capacitor, half of it has a dielectric, and half of it does not have a dielectric. What does that mean? It means that this capacitor will be now split into two. One will be having a dielectric, so this one will be a capacitance when there's the dielectric, and this will be capacitance when there's no dielectric, and they will be in parallel. So with that illustration, you can now go ahead and answer our question. So before displacing the dielectric, the capacitance is given by this. I think we know this formula. This is a formula when there's a dielectric in between the plates. Therefore, the initial charge is CV, where C is this and V is here, which is this. So when I combine, I'll come up with this. That is the initial charge, where A is the area of overlap and D is the plate separation. Now what about when the dielectric is withdrawn halfway? So now we have two capacitors in parallel. Therefore, total capacitance will be got by adding. So this is C2. So when I add, I'll come up with, now the area area now will be a half A, because it is half, this one is covering half the capacitance and this one is also covering half the capacitance. So simplify, this gives you this and this gives you that, and when I add these ones you realize that there's some things in common. The whole of this is also found here because there is this and also this. So you pull it out and this here remain with 1, here remain with epsilon r. Therefore the final charge is C prime V, substitute for C prime and substitute for V. Simplify to give you this. But we know that charge is proportional to current. Therefore, Q initial over Q final is equal to I initial over I final. So I'll come and substitute for Q initial, which was going in previous slide, over Q final, and to be equal to I initial over I final. Then from there you realize that this one is going to cancel, this AV is going to cancel, and this D is going to cancel. So what does that mean? It means that you are going to remain, numerator will remain with epsilon r. Denominator, there is this a half, and there is also this bracket which is here. Then from there I'm going to take the whole of this side, and this side I'm cross multiplying. Then from there I'll bring this to this side to give you this line and open the bracket. Then from there my aim is to make epsilon r the subject, so I'll bring the whole of this side to give you this line. Then epsilon r is common, factorize it out, then make it the subject, and that's what they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on current electricity. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who is not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.